Welcome back to Geometry Classroom. Today we'll start a new section called probability. In this lesson, we'll talk about theoretical and experimental probability. In this lesson, we define theoretical and experimental probability, and we'll learn how to find the theoretical and experimental probability of an event. Now, first, let's define the probability. What is a probability? The probability of an event is a numerical value from 0 to 1 that measures the likelihood of an event. We can write the probability of an event as a fraction, decimal, or percent. Now, an event is a single outcome or a group of outcomes, right? In this diagram, I prepare for you a few special cases, right? Now, if the probability of an event is 0, right, that event is impossible to occur, right? Or simply cannot occur. If the probability of an event is 0.5 or 50%, that event may or may not occur evenly. When the probability of an event is 1, that event certain will occur. It's 100% that will occur. Good. In this slide, we have a few vocabulary words related to probabilities. First, what is an outcome? An outcome is one possible result of an event. For example, when you roll a dice, right? For example, rolling 5, right? When you roll a dice is one event, right? Is a possible outcome of rolling a dice. When you roll a 7, right? Is a possible outcome of rolling 2 dice, right? And so on. Sample space is the list of all possible outcomes of an event, right? For example, when you you roll a die, right? Dice. What possible outcomes could be 1, 2, 3, 4, 5, and 6, right? These numbers could be rolled. Yeah, listing all these numbers or all of these possible outcomes means listing sample space. Also, the size of the sample space is the total number of possible outcomes. All you need to do is to count how many such events are. When you roll a dice, you'll have 6 possible outcomes. That's the size of the sample space. When you roll 2 dice, you'll be surprised, but the size of sample space would be 36. And I will show you. For example, here, yeah? When you roll 2 dice, you may have on one dice 1, on the other one also 1. But in the same time, you may have 1 and 2, 1 and 3, 1 and 4, and so on. So, the total possible number of favorable outcomes, or the number of possible outcomes, is 36. Good. A success is an outcome that we want to measure. A failure is an outcome that we do not want to measure. So failures would be sample space minus successes. Or successes, right, is the sample space minus failure. Now, let's define now theoretical probability. Yeah. So, if the outcomes in a sample are equally likely to occur, the theoretical probability of an event is the ratio of the number of favorable outcomes, which is the number of outcomes corresponding to the event, to the number of possible outcomes, right? So that's the formula. Is the ratio of number of favorable or desired outcomes over total number of possible outcomes. Again, this is a fraction larger than 0, but less than 1. Don't forget. Also, experimental probability of an event measures the likelihood that the event occurs based on the actual results of an experiment. It is given by the formula given below. Yeah? So, probability of an event is the ratio of the number of times that event occur over total number of trials. Now, is a difference between theoretical probability and experimental probability. And what is the difference? The theoretical probability is what we should expect to happen. Yes? Or what should expect to happen. While the experimental probability is what is actually happens. Now, experimental probability is the result of an experiment or simulation after a large number of times or trials. In fact, I would say the experimental probability is a kind of real probability. Is the probability that happens in reality, right? While theoretical probability is what is expected to happen based on the possible outcomes, assuming they are equally likely event. In reality, this situation never happens, or it's less likely to happen. Yeah? Good? Another vocabulary, that word that is important, is complement of an event. Represents possible outcomes that are not in the event, right? For example, if event A occurs 70% of the time, it will fail to occur 30% of the time, right? And the event that event A occurs, right, is the event itself, right? But its complement is the event that A will not occur, right? So we have a formula for this. So the probability of event A, right, plus probability of its complement is always 1. Yes? Or the probability of complement of an event would be 1 minus the probability of event A. That's why we call them complementary or complement. Good? Now, in next two slides, let's have a few examples of theoretical and experimental probability. For example, what is the theoretical probability that an even number will be rolled on a number cube, right? Now, remember, a number cube or a dice is a cube with 6 faces. On each face there is a number, right? Now, let's list all possible outcomes. 1, 2, 3, 4, 5, 6, right? It says, what is the theoretical probability that an even number will be rolled? Now, what are the even numbers? The even numbers are 2, 4, and 6, right? What is the probability of getting an even number, right? Is the ratio of number of favorable outcomes, assuming they are equally likely, yes? And we have 3 such favorable events, so 3 would be on top, and over the total number of events, which is 6, because we have 6 possible outcomes. Now, if we simplify this fraction, you'll get 1/2, or 50%. So that's the probability of getting an even number when you roll a dice as an event. Good. Next, what was the experimental probability of how many times an even number was actually rolled using the table, right? Now, this time we have to find the experimental probability. Is the probability that result is a result of an experiment, right? Here is the number of trials, right? Here is the numbers on a number cube, right? In other words, how we read this table? When you roll the dice as an experiment, right? Number 1 showed up or appeared 8 times. When you roll these dice, number 2 appeared 3 times, 3 9 times, 4 6 times, and so on, right? Good. Now, first, let's find what is the total number of trials. The total number of trials, if you add these numbers, would be 36, right? Now, what are the even numbers? Are, again, 2, 4, and 6, right? Now, to find the experimental probability of having an even number, right, in this case, we have to find the total number of favorable trials, right, which is, for number 2, we had 3 times, right? For number 4, 6 times. For number 6, 6 times. What we supposed to do with these numbers? We have to add them, yeah? 3 plus 6 is 9, plus 6 is 15. So that's the total number of favorable trials. And, of course, in the denominator, we should write the total number of trials, which is 36, right? So we can simplify this fraction. 3 is the common factor. So we're going to have 5 over 12, right? So that's the experimental probability. As we can see, there is a difference between these two probabilities, right? Another problem is if you roll a number cube 36 times, how many times would would you expect to roll the number 1? Now, we know when we roll dice 6 times, number 1, yes, number 1 appeared one time, right? Now, but if you roll a dice 36 times, right? How many times we should expect, right? We should expect to have number 1. Remember, we should expect means theoretical, right? Theoretical. So, we have a number of trials, 6 more than 6, right? So, we should expect number 1, right, to appear 6 times, right? 6 more times than the initial experiment. So, here should be 6 times. Now, number 4, how many times did you actually roll the number 1 in the experiment? Of course, the number 1 appeared 8 times, right? 8 times. Good. 3 more examples that are related to problems 1 through 4 in the previous slide. What is the theoretical probability for rolling a number greater than 4? Yes? Remember, the key word here is theoretical. Yes? Now, as we know, when we roll a dice, we should expect to have numbers 1, 2, 3, 4, 5, and 6, right? Now, the probability of getting a number larger than 4, right, would be the ratio of the total number of favorable events, right, which is 2, right, because 5 and 6 are the only numbers larger than 4, right? So, how many favorable outcomes could be? Only 2. So, 2 is at the top of the fraction, or in the numerator of the fraction. Now, in the denominator, we should have the total number of possible outcomes, which is 6, right? So, you're going to have 2 over 6. If we simplify this fraction, you'll get 1/3. Now, 6. What was the experimental probability of rolling a number greater than 4? Now, to find this experimental probability, of course, we should go back to the table, right? Now, what numbers are greater than 4? Of course, 5 and 6. How many times 5 appeared? 4 times. How many times 6 appeared? 6. So, to get the total of favorable trials, we should add these two. 4 plus 6 is 10. But the total number of trials was 36, right? So, we should have here 10, which is the total number of favorable trials, over 36. Now, if we simplify this fraction, of course, you'll get 5 over 18. Yes? As we can see again, the theoretical probability and experimental probability are different. Yeah, this is what we should expect to happen, but this probability is what is actually happens. Now, what is the difference between theoretical probability and experimental probability? Is theoretical probability equals what should happen and experimental probability is what is actually happens or happening. Yeah? Yes? This is all we have for today. In the next lesson, we'll talk about geometric probability. For now, thank you for watching my video.